Hi friends, I am Samay Chowgule, Department of Mathematics. Here I am sending the video on number theory. In that, we will start from fundamental theorem of arithmetic. The statement of the theorem is each natural number n greater than 1 can be expressed as product of primes in one and only one way, except for order of the factor. That will prove here. That is what we have to take any natural number n greater than 1. We have to express that in the form of product of primes. Here what is given except the order of factors means the factors may be in any order. So that is we'll take let n be any natural number greater than 1. If see n has a prime factor, as this n is a natural number, we'll say that it has one prime factor, say p1. That is what factor means, that p1 divides n. Therefore, there is, according to definition of divisibility, as p1 divides n, there is an integer n1 such that n is equal to n1 into p1. That is equation 1, where n is greater than n1. See, we are writing this equation 1 by using definition of divisibility. As this n1 is a factor, the remainder is 0. So therefore, n equal to n1 into p1. Then if n1 is equal to 1, then n equal to p1. If suppose this whatever quotient we got, that is n1, if that n1 is equal to 1, then n equal to p1, that is n is a prime number. Suppose if n1 is greater than 1, then n1 has again a prime factor, say that prime factor is p2. If n1 is greater than 1, then it should have again a prime factor, that prime factor will take as a p2. Again, as n1 is a prime that p2 is a prime factor of n1, then according to definition of divisibility, again there is an n2 such that n1 is equal to n2 into p2, where n1 is greater than n2. Now putting this value in equation, value of n1 in equation 1, we get n equal to p1 p2 into n2, where n greater than n1 greater than n2. Again, suppose if n2 equal to 1, then n equal to p1 into p2. That is what n is. Both p1 and p2 are prime numbers, so I have expressed n in the form of product of primes. That n is a product of primes p1 and p2. If n2 is greater than 1, again we have to continue the process. That is what, if n2 is greater than 1, then it has again a prime factor, so that prime factor may be p3. Then what we have to write, according to definition of divisibility, again there is another one number, that number will take as n3, so that n2 is equal to n3 into p3. That p3 you have taken as a prime factor. So again that n2 you have to substitute in this equation. Here what we have, n equal to p1 p2 into n2 we have. Here we have to replace the n2 value. So this process you have to continue, but this process must end after finite number of steps. Because why this ends? Because whatever these numbers n1, n2, n3, so on, these numbers are there, those numbers goes on decreasing. See here, n1 greater than n2, n2 greater than n3, and so on, these numbers goes on decreasing. At the final step where we are getting that number is equal to 0, so that at that step we are getting, our steps will be stopped. So this must end after finite number of steps. Therefore, the register primes p1, p2, so on up to pr. Up to rth step exists, r plus 1th step not exist, so we'll take up to pr such that n equal to n1, p1, p2, p3, so on up to pr. That is equation 3. You see here, n equal to p1, p2, p3, pr we got. Each of these pi's are the prime numbers, so therefore we have expressed n as a product of primes. Now of course these primes p1, p2, so on up to pr need not be all distinct. These may be repeated primes, but each of these numbers are the prime numbers. So next what we need to prove uniqueness. In the statement it is given, these natural number n can be expressed as a product of primes in unique way, or one and only one way. So once we have expressed this as a product of primes, next we need to prove it is unique. So what we will assume here, if possible, assume that there exists another one possibility of expression of that natural number n, where n equal to q1, q2, q3, so on up to qs. Each of these numbers are the prime numbers. Each of these numbers Q1, Q2, so on up to Qs are the prime numbers. Now be an alternative expression. This expression, equation 4, is an alternative expression of n as a product of primes are taken. Then from equation 3 and 4. See, in equation 3 left side n, equation 4 left side n, so right side must be equal. So we are writing P1, P2, P3, so on up to Pr is equal to Q1, Q2, Q3, so on up to Qs. Now these factors are equal. P1 multiply up to PR, Q1, Q2, so on up to Qs, these both are equal. But it is not necessary to say that here these are a unique factor, unique expression we can't say here. Because see here, the multiplication of two numbers, you may write the multiplication of two numbers if you want to take. Now see, if I write 2 into 3, two into 3 into 2, yes, that is equal to 3 into 4. 3 into 4. So what you are getting? This both side numbers is equal to 12 itself, but the expressions are not same. Yes, like this, we will assume that these two are the expressions P1 to PR and Q1 to Qs we have taken. Now to show these two are equal, these two are same, not equal, they are equal, but we need to show these two are same. So what do we need to prove here? P1 equal to Q1, P2 equal to Q2, P3 equal to Q3, and so on, PR equal to Qs. Yes, and what we need to prove? These are equal to S also we have to prove. P1 equal to Q1, P2 equal to Q2, and so on, PR equal to Qs also we need to prove here. So that we need to prove R equal to S. So that, see, from equation 5 it shows that P1 is the factor of the product P1, P2, sorry, Q1, Q2, so on up to Qs. As these left side, these the numbers are prime numbers, right side also these numbers are prime numbers. Now this is the whole product is divisible by P1. So P1 is one factor of this. So P1 must divide sum of these numbers, prime numbers. See, these are all of these are prime numbers. The product is there. This P1 divides this product means P1 divides at least one prime number. Know that prime number will take as a Q1. So P1 divides Q1. Now see, as Q1 is the prime number, this here P1 divides prime Q1, and Q1 is the prime number means it has divisors only either 1 or the number itself. Now P1 is the divisor of Q1 means that P1 must be equal to 1 or P1 equal to Q1. But here P1 is not equal to 1 because we have already that P1 is a prime number. So therefore P1 must be equal to Q1. So one condition we got here, P1 equal to Q1. So the next, by cancellation law, apply the cancellation law for that equation 5. Both sides P1 and Q1 get cancels because those are equal here. So we got P2, P3, so on up to PR equal to Q2, Q3, so on up to Qs. That is equation 6. Now similarly as before, we have P2 must be equal to the sum of the prime numbers Q1, Q2, Q3, so on up to Qs. As because again that P2 must divide this whole product means P2 must divide any one of the prime factors. So that factor will take as a Q2 itself. So as P2 divides Q2 and Q2 is a prime number, that must be equal to either 1 or Q2. So therefore we'll get P2 equal to Q2. So what we are getting? P2 equal to Q2. So that equation 6, again apply cancellation law for equation 6. P2 and Q2 get cancels. We are getting P3, so P3, P4, so on up to PR is equal to Q3, Q4, so on up to Qs. Proceeding in this way, we are getting P3 equal to Q3, P4 equal to Q4, and so on. But here, generally, we can't write PR equal to Qs. Yes, here P1 equal to P2, P3 equal to Q3, P1 equal to Q1, P2 equal to Q2, P3 equal to Q3, P4 equal to Q4, and so on. If you want to write PR equal to Qs, PR equal to QR, it is true. PR equal to QR, PS equal to Qs. Now to write PR equal to Qs, we need to prove R is equal to S. So that is important here. So finally, we need to prove that R equal to S. So to prove this R equal to S, we need to prove, yes, we know by law of trichotomy, for any two numbers R and S, either R less than S or R greater than S or R equal to S. Any one holds at a time, only one will hold. So therefore, to prove this, we will assume here is that R is greater than S, that will check. Then is that R is less than S, that will check. Both will fail, so we say R is equal to S here. So first of all, we will assume that let R is greater than S. It means in this expression, P1 equal to P1 into P2 into P3, so on up to Q1 into Q3 into Q4 up to Qs. So PR we have up to PR we have taken, right side up to Qs. Suppose if this R is greater than S, for example, if I take R equal to 10 and S equal to 6, yes, so what you are getting, left side P1, P2, P3, so on up to P6, P7, P8, P9, P10. Right side Q1, Q2, Q3, so on up to only Q6. So here that 6 is repeated. PS we have repeated here. PS, QS. S equal to 6 we have taken. So P6 will come. So what will happen? P1 equal to Q1. P2 equal to Q2. P3 equal to Q3. P4 equal to Q4. So on up to what? P6 equal to Q6. P6 equal to Q6. So remaining P7, P8, P9, P10. These numbers remains. So that we will replace here. So what we will do? These numbers will replace. Right side numbers Q1 equal to P1, Q2 equal to P2, so on up to QS equal to PS, that will replace. And remaining numbers, left side remaining numbers as it is. Now dividing throughout by, now this expression we have, for this expression dividing throughout by P1, P2, P3, so on up to PS, we are getting left side these up to PS term get cancels. Remaining terms are PS plus 1, PS plus 2, so on up to PR. It means 6 terms get cancels. P7, P8, P9, P10. These terms remains. Right side all the terms will get cancels. Remaining 1. So but this is impossible because each factors on LHS being a prime. See, each factor in LHS, that is PS plus 1, PS plus 2, so on up to PR. These are, each of these numbers are prime numbers. Being a prime numbers, each number is greater than 1. So the number is greater than 1, each number is greater than 1, and the product is equal to 1. It is not true. So therefore, R greater than S is not true here. Similarly, I have written here R less than S is also not true. See what will happen in that case? If you take R is less than S, then in this equation what we have to write? Left side we are getting P1, P2, P3, so on up to PR. And right side Q1, Q2, Q3, so on up to QR, QR plus 1, QR plus 2, so on up to QS, because we have R is less than S. So here what you have to do? Again, we have to replace, and these left side term will get cancelled. P1, P2, so on up to PR, these terms will get cancelled. Left side it remains 1. Right side we are getting QR plus 1, QR plus 2, so on up to QS. Again, the product is not equal to 1. As being a prime numbers, the product is not equal to 1. Hence, R is less than S is also not true. So therefore, R must be equal to S by using law of trichotomy. So therefore, the two whatever decompositions you have written, P1 to PR and Q1 to QS, both are identical or both are same. So therefore, remember, any natural number n greater than 1 can be expressed as product of primes in one and only one way. Remember, the prime factors may be repeated. Prime factors may be repeated here, not necessarily these are all are distinct. May be distinct, may not be distinct. Now comes the standard form. Yes, as we know, the number n1 is said to be expressed in the standard form. Yes, we know that any natural number n can be expressed in product of primes. Now, when it is said to be expressed in standard form, that you have to check. See, the prime number, we have expressed the numbers in the form of product of primes. The prime numbers may be repeated. Now, what we have to do? The repeated primes we have to write in the form of power. So that n equal to P1 raised to alpha 1, P2 raised to alpha 2, so on up to Pk raised to alpha k, where P1, P2, so on up to Pk are distinct prime factors of n, and alpha I greater than or equal to 1. Now in this expression what we have, each of these factors P1, P2, so on up to Pk, these are distinct primes because repeated primes are written in the form of the power. See for example, see here, express 29,645 in terms of their prime factors. We are expressing the standard form itself here. So see what you have to do, we have to take this 29,645, take factorization, only you have to go on dividing by prime numbers. First check for 2, 3 and then go for 5. It is the I have given here prime factorization. 5 divided by 5, 7, 7, 11 and 11. So we are getting 29,645 is equal to 5 into 7 into 7 into 11 into 11. Each of these prime numbers are, each of these factors are the prime numbers here. Now see, this number, natural number n, is expressed in the form of product of primes. Here the prime numbers are repeated. Now repeated primes will write as a, see 5 as it is, 5 into 7 into 7, 7 square into 11 square. Now observe this equation. Here 5, 7, 11. These are the three distinct primes. This power may be not necessarily it is the prime number. So therefore any that alpha I is any greater than number greater than or equal to 1. So we are getting 5 into 7 square into 11 square. That is the standard form for 29,645. Similarly, I have given direct answer for this next number. You can try this. That is, I given the number 1579663800. For that, this you are getting the answer here. You try that. Next, the very important concept, which is most useful in the even in the competitive examinations also. These type of finding the number and sum of divisors or of finding number of factors or sum of factors of any natural number they will ask you. So see the number and sum of divisors of a composite number n. So n is any composite number here. N is any composite number. It means composite number means it has a divisors other than 1 and itself. If it is a prime, then only 2 divisors. So no question of finding the number of divisors. So therefore, we have to consider that n as a composite number. So here d of n denotes the total number of divisors of that composite number n. Total number of divisors of composite number n is denoted by d of n. Then we know that by fundamental theorem of arithmetic, n can be expressed as a product of primes, and that primes you have taken as n equal to alpha 1 raised to p1 raised to alpha 1, p2 raised to alpha 2, so on up to pk raised to alpha k, where p1 to pk are distinct primes and alpha 1, alpha 2, alpha k are non-negative integers. Now see, since p1 is a prime number, the only divisors of p1 raised to alpha 1 are 1, p1, p1 square, so on up to p1 raised to alpha 1. These are the only divisors of p1. As this p1 is a prime number, the only divisors of p1 raised to alpha 1 are 1, p1, p1 square, and so on up to p1 raised to alpha 1. See for example, if I take 2 as a prime number and 2 cube, I will consider another number as a 2 cube. Then what are the divisors? 2 cube means it is 8. Divisors of 8 are 1, 2, 4 and 8. These are the divisors. So that is what? 1, 2, 2, that is p1 raised to 1, 4, p1 is 2, 2 square, and 8, that is 2 cube. So like that, only the divisors of p1 raised to alpha 1 are 1, p1, p1 square, so on up to p1 raised to alpha 1. These are how many number? These divisors of p1 raised to alpha 1 are alpha 1 plus 1 in number, because this is 1, it is p1 raised to 0, p1 raised to 1, p1 raised to 2, so on up to p1 raised to alpha 1. 1, 2, 3, third term is p square, p1 square. So that this is alpha 1 plus 1th term it is. So therefore, the total number of divisors of p1 raised to alpha 1 are alpha 1 plus 1. Similarly, in the same concept, we are getting total number of divisors of p1 raised to alpha 2 is equal to alpha 2 plus 1, pk raised to alpha k is equal to alpha k plus 1. Sorry, it is p2 raised to alpha 2. The number of divisors of p2 raised to alpha 2 equal to alpha 2 plus 1, and similarly pk raised to alpha k is alpha k plus 1. Therefore, total number of divisors of n is 1, p1 raised to alpha 1, p2 raised to alpha 2, so on up to pk raised to alpha k. So for each of these factors, you have find a total number of divisors. You have to multiply that. So that is n equal to this number. So its divisors are these one. Therefore, D of n, total number of divisors of n, is equal to alpha 1 plus 1, alpha 2 plus 1, so on up to alpha k plus 1. So that is what, if you express n in the form of a prime factorization like this in the standard form, then the number of divisors of n equal to alpha 1 plus 1 into alpha 2 plus 1, so on up to alpha k plus 1. Now, the sum of divisors of n is denoted by sigma n. So the number of divisors we've taken as a D of n, now we'll take sum of divisors as a sigma n. Since P1 is a prime number, again, same. These are the divisors P1, 1, P1, P1 square, so on up to P1 raised to alpha 1. These are the all divisors of that P1 raised to alpha 1. But here we need sum of divisors. So we'll add all these divisors. P1 raised to alpha 1. Its divisor sum 1 plus P1 square, so on up to P1 raised to alpha 1. Now see, this is right side is in GP with a equal to 1. So therefore, applying the formula of sum of first n terms of a GP, we are getting this sum is equal to P1 raised to alpha 1 plus 1 minus 1 divided by P1 minus 1. Similarly, the sum of divisors of P2 raised to alpha 2 is 1 into P2 raised to alpha 2 plus 1 minus 1 divided by P2 minus 1. In general, the sum of divisors of Pk raised to alpha k is equal to 1 into Pk raised to alpha k plus 1 minus 1 divided by Pk minus 1. Therefore, sigma n, the sum of divisors of n, that is equal to P1 raised to alpha 1 into P2 raised to alpha 2, so on up to Pk raised to alpha k. That is equal to sigma n is equal to alpha 1, P1 raised to alpha 1 plus 1 minus 1 divided by P1 minus 1 into P2 raised to alpha 2 plus 1 minus 1 divided by P2 minus 1, so on Pk raised to alpha k plus 1 minus 1 divided by Pk minus 1. So this is what the sum of divisors, formula for finding the sum of divisors, and this formula is for finding the total number of divisors. See, we have taken the examples here. Find the number and sum of divisors of 600. The number 600 is given. We need to find the number and sum of divisors of 600. So first we need to express the 600 in standard form. So we got that 600 is equal to 2 cube 3 raised to 1 plus into 5 square. It is equal to 600. I have given a factorization also. So here compare this with the standard form. P1 equal to 2, P2 equal to 3, and P3 equal to 5. Alpha 1 equal to 3, alpha 2 equal to 1, alpha 3 equal to 2. Substitute D of n, total number of divisors, that is equal to alpha 1 plus 1 into alpha 2 plus 1 into alpha 3 plus 1. So that is 3 plus 1, 1 plus 1, 2 plus 1. Multiplying, we get 24. So total number of divisors of 600 equal to 24. Now we'll see what is sum of all those divisors. That is sigma n is equal to sum of divisors of n, that is equal to 600. So formula is P1 raised to alpha 1 plus 1 minus 1 divided by P1 minus 1 into P2 raised to alpha 2 plus 1 minus 1 divided by P2 minus 1 into P3 raised to alpha 3 plus 1 minus 1 divided by P3 minus 1. Substituting the values and simplifying, we are getting 1860. This is